Hello and welcome to our lesson 6.1 over properties and attributes of polygons. Today's objective will be to classify polygons based on their sides and angles, find and use the measures of interior and exterior angles of polygons. So, before we begin, make sure you have done the two things we talked about in class. That your vocab terms are all written down in your vocab notebook, and that you have done this warm-up. When you are ready to check your answers for the warm-up, you may restart the video. If you're already ready, then here are the answers you should get. A blank is a three-sided polygon. That would be a triangle. A four-sided polygon is a quadrilateral. If you wrote square or rectangle, those are specific quadrilaterals that we will get to later, but quadrilateral is the word we should have. And number 3, when we evaluate this for n, plugging in 6 for n, 6 minus 4 is 2, 2 times 12 is 24. 6 minus 3 is 3, 3 times 90 is 270. And in this equation we need to solve for a, so we're going to add up all the coefficients of these because these are all like terms. 12 plus 4 plus 9, and divide by that number, and we get 4. A is 4. All right, again, here are your objectives that I mentioned just a moment ago. And here's the vocabulary that we will discuss in this lesson: side of a polygon, vertex of a polygon, diagonal, regular polygon, concave, and convex. Now remember, we defined what a polygon was back in lesson 2.4. All right, now we're going to learn about the parts of a polygon and about ways to classify them. So you have this diagram in your notes. The side of the polygon is the segment. One of the segments forming the polygon is called the side. The common endpoint of two sides is called a vertex. And a segment that connects two non-consecutive vertices is called a diagonal. This is only one diagonal we could have. If I connected A and D, that'd be a diagonal. If I connected EB or EC, those are also diagonals. We can name a polygon by the number of its sides. This table shows some of the most common polygons. 3-sided is called a triangle. 4 sides is called a quadrilateral. 5-sided polygon is a pentagon. 6 sides is hexagon. 7 sides is heptagon. Make sure you keep those two distinct. 8 sides, you know, is an octagon. 9 sides might be newer to you. That's called a nonagon. 10 sides is a decagon. And then 12 sides is another common one we will use, called a dodecagon. And then anything else with n representing the number of sides it has, we just call an n-sided polygon. We do not say n-gon or n-gon. We call it n-sided polygon. All right, and n represents the number of sides. And these are just some of the most common ones. You may notice there's some that aren't there. Obviously, we would just call those, using the number of sides for n-sided polygon. Remember, a polygon is a closed plane figure formed by 3 or more segments that intersect only at their endpoints. So the things that make up a polygon are segments, which are parts of lines, insinuating they must be parts of straight lines, not curves. So in these examples, we're going to tell whether or not this is a polygon. If it is, we should be able to classify it by its number of sides. Okay, if you look at part A, that's a polygon, and it's called a nonagon. There are 9 sides. If you counted them, there are 9. This, while it represents a specific shape, is in fact a polygon. It's made up of segments, and there are 7 of these segments, so it's a heptagon. This shape is not a polygon. These are made of 2 curves, 2 portions of circles. So we say it's not a polygon, or just write no. This shape, we do not connect these two. There's nothing to connect these. These are a set of segments, but they are not. This is not a closed plane figure. That's the part of the definition that we're missing. This is not a closed plane figure, so it's not a polygon. This is a closed plane figure made up of segments, so it is a polygon with 6 sides, which is a hexagon. And lastly, 3 of these sides are formed by segments, and it is a closed plane figure, but the 4th side, as it were, is not a segment at all, but part of a circle. So this is not a polygon. All the sides in a polygon, if they are congruent, make up an equilateral polygon. Remember, we talked about that with triangles. If all the angles are congruent, we call it an equiangular polygon. And then a regular polygon is any one that is both equilateral and equiangular. Now with triangles, if they were equilateral, they had to be equiangular. But with any other polygon, that will not always be the case. So we need to specify that in a polygon with greater number of sides than 3, we could have a regular polygon only if they're both equilateral and equiangular. If a polygon is not regular, it's called irregular. And then we can also classify a polygon as concave or convex. And you might remember in science class talking about lenses that could be either concave or convex. And remember what those shapes look like. That will help you determine whether a polygon is concave or convex. Here's our definitions for concave and convex. If any part of a diagonal contains points in the exterior, so if I can draw a diagonal that actually goes outside the closed plane figure like this, that's concave because part of the figure has caved in. That's a way to remember that. But if all the diagonals we draw go through only the interior points, then it's considered convex. Or it might be easier to think of, if it's not concave, then it is convex. So let's look at example 2, classifying as either concave or convex and as regular or irregular. So in this, we have all the sides are congruent, but these markings show that these angles are congruent, while these angles are congruent. Not all 4 are congruent. So while it is equilateral, it is not equiangular, so that we say this is irregular. And because all the diagonals would go through the interior, we say it's convex. In this case, all of the angles are right angles, but we're forgetting these angles formed here. They are not going to measure 90 degrees like the rest because they go more than 180 degrees. Because I could draw a diagonal from here to here through the exterior, this is concave, and it is irregular. We also don't know anything about the side lengths measurement. Another reason for this to be irregular, and then these make it concave. Here we have a quadrilateral where all 4 sides are congruent and all 4 angles are right angles, which are also congruent, and so it is regular and convex. Here we have a pentagon, 5 sides, where all 5 sides are congruent and all 5 angles are congruent, so this is also regular and convex. In this case, we have 2 congruent angles here, but none of the other angles are congruent, so this is not equiangular, so it cannot be regular. This is irregular. And if I were to draw this diagonal, that goes to the exterior, so this is concave. Irregular and concave. Now let's talk about finding the sum of the interior angle measures of a convex polygon. From now on, we are only talking about convex polygons in this lesson. We want to draw all the possible diagonals from one vertex of a polygon to help us see this. So let's start with a triangle, which has 3 sides, a quadrilateral, which has 4 sides, a pentagon, which has 5 sides, and a hexagon, which has 6 sides. I'm going to pick one vertex and draw all possible diagonals. Well, within a triangle, you cannot draw diagonals because each of the other vertices would be considered consecutive with the one we're choosing. So in a triangle, there's only one triangle created by diagonals. In a quadrilateral, however, if I just drew the diagonals from one vertex only, that only leaves me with one diagonal, leaving 2 separate triangles. So within a quadrilateral, we could have 2 distinct triangles. But in a pentagon, there are 2 different diagonals I could draw, so I have 3 distinct triangles. And in a hexagon, there are 4 distinct triangles. Now you might remember that the sum of the angle measures of a triangle add up to 180 degrees. Well, there are 2 triangles within this quadrilateral, so there are 2 180-degree sums. And in the pentagon, there are 3 180-degree sums. And in the hexagon, there are 4 180-degree sums. So let's look at the following table. And remember, by the triangle sum theorem, the sum of interior angle measures of a triangle is 180 degrees. So we have this table we can get using these 4 figures. So if we have 3 sides of our polygon, that's a triangle. There's only one of the triangles, so our sum of the interior angle measures would still just be 180 degrees, or 180 degrees total. But in a quadrilateral, these two triangles give us two 180-degree sums, which is 360. And for 5, we have 3 triangles, so we get 540 total. For 6, we have 4 triangles, so we get 720 total. And so for any n-sided polygon, the number of triangles within that would have to be the number of sides minus 2. That's the pattern we recognize. If the number of sides is 3, there's 1 triangle. 3 minus 2 is 1. If the number of sides is 4, we have 2 triangles. 4 minus 2 is 2. For 5 sides, we get 3 triangles because 5 minus 2 is 3. 6 minus 2 is 4. And we could go on and make a more extensive list based on the number of sides. But this formula will help us. So the sum of the interior angle measures of any sided polygon is the number of sides minus 2 times 180. So we get this theorem. The sum of the interior angle measures of a convex polygon with n sides is n minus 2 parentheses times 180. So let's try some examples. Let's say we're finding the sum of the interior angle measures of a convex heptagon. Remember, heptagon means there are 7 sides. So we're going to use this formula, n minus 2 times 180. A heptagon has 7 sides, so we're going to substitute 7 for n. When we simplify, we get 900 degrees total. Part B, same kind of problem, only they've given you different algebraic expressions for the measurements. Well, look at how many sides there are. This is a pentagon. If we use that same formula, we're going to plug in 5 for the number of sides. And when we simplify, the total should be 540 degrees. So all 5 of these angles should add up to 540 degrees. Well, that allows us to write an equation like this. The measure of all 5 angles should equal 540, so we substitute in the values that we know. 35c, 18c, 32c, 32c, and 18c should add up to 540. When we combine all like terms, like we did on one of our problems from our warm-up, we get 135c equals 540. Well, now we just divide both sides by 135 to find the value of c. c is 4. So to find each angle measure, we need only plug in 4 for c. So the measure of angle A is 35 times 4, or 140 degrees. B and E are 18 times 4, which is 72 degrees. C and D are 32 times 4, which is 128 degrees. So these 3 measurements represent all 5 angle measures. In part C and D, I'm going to let you try and work these out, and then we'll check our answers together. Pause the video if you need more time. Alright, hopefully you've worked this out, and we should get something like this. Using this formula for a 15-sided polygon, 15 minus 2 times 180 is 2,340. Part D, finding the measure of each interior angle of a regular decagon means you first find the sum. n minus 2 is 1 times 180. 10 minus 2 is 8 times 180 is 1,440, so they should all add up to that, but each angle is the same because it's regular. So we're going to divide 1,440 by 10 congruent angles, which is 144 degrees. Now to talk about the exterior angles, what they would add up to, you'll notice that no matter how many sides the polygon has, the exterior angles always add up to 360 degrees. The sum of the exterior angle measures, one angle at each vertex of a convex polygon, is 360 degrees. So in example 4, we're going to use that fact to find angle measures. First, find the measure of each exterior angle of a regular dodecagon. You'll remember dodecagon means 12 sides. So there are 12 congruent exterior angles. So the sum of all 12 would be 360. So if I divide 360 by 12, each angle must be 30 degrees. In this example, we are given expressions for each one. Again, if I add all of these up, they would equal 360. So when I combine like terms, I get 120b equals 360. Divide by 120, and b is 3. In this last example, why don't you take a moment to see what answer you get and go from there. Pause the video if you need more time. Alright, you'll see that if we add up these terms and combine them and divide by 24, r is